lemma, also known as summation by parts, is a discrete analog of integration by parts. For a set of polynomials capital P sub k of x from k equals 0 to n with coefficients in a field f, we'll say that this set satisfies star n if for any/every polynomial f of x of degree less than or equal to n, this function is constant with respect to x. So far, this is just definition. An arbitrary set of polynomials with coefficients in f, like this, where the relation capital P sub k of x equals this sum. This will define lowercase p sub j's. And the set capital P sub k of x from k equals 0 to n will satisfy star n if and only if for any/every polynomial f of y of degree less than or equal to n, we have this equality. And this is a bit surprising how this equality would be equivalent to this function being constant with respect to x. So let's see why that is. So recall Abel's lemma, aka summation by parts, which we'll denote by capital A sub n, where in its general form it says that given a ring R, a left R module M, a subset of R, and capital G sub k equals this sum, then we have this equality here. So already we can see that Abel's lemma is reminiscent of the lemma that we're trying to prove. We have capital G being defined in terms of these lowercase g's. And similarly, we have these lowercase p's, which are defined in terms of these capital P's. Adding an index, we can slightly generalize this. So instead of working with f sub k, g sub j, capital G sub k, we can work with f sub k comma I, g sub j comma I, capital G sub k comma I. And then we can add summons on the left and right hand side and sum from I equals 0 up to m. So that gives us this result here, which has several components. And we can give some notation to these components to make the bookkeeping a little bit easier to keep track of. So on this left-hand side, we can call that capital Z sub n comma m. And similarly, we'll give names to these other parts. So x sub n comma m, we can have that set equal to this. Similarly for these y terms. And when we put it all together, we're able to rewrite our generalization as a sub n comma m. That's our generalized Abel's lemma. Tells us that z is equal to x plus the difference of these y terms. We're not quite interested in the full generalization of Abel's lemma. We're particularly interested in the case where R is a field, which means that these little g sub k comma I are field elements. P sub k of x we can have equal to this, but this really defines the lowercase g's. The lowercase p's are defined in terms of the capital P's. So capital P's define the lowercase p's, and then these lowercase p's will define these lowercase g's. These lowercase g's define the capital G. Our left R module M is polynomials in variables x and y with coefficients in the field f. We'll consider f of x some polynomial in x with coefficients in the field f. And with this, we can define f sub k comma I as such. And the motivation for this is so that these components simplify nicely. So we'll witness that. This first line here, z sub nm equals this double sum. This is just definition. So that's just definition right there. And then this next part here in the equality, we're switching the order of the summons. This is a finite sum, so we're certainly allowed to rearrange the order of our summons here. And once we do that, we can put brackets around this part, and then we can recognize that this is none other than p sub k of x plus k. So this simplifies to this. And there's similar simplifications which take place for x and both of these y parts. With the process is similar in the sense that we rearrange the order of the summons and we lump terms together. And we'll get these nice simplifications. Another observation that we can make from this generalized Bell's lemma is that z is equal to x if and only if both of these y components are equal. And we can have notation for this too. This left-hand side equality we can refer to as B1. And this equality on the right-hand side we can refer to as B2. So what we're saying is B1 is equivalent to B2. And this doesn't make use of any of these simplifications just yet, but we can do that now. So B1 has z equal to x. Referring to our simplifications, this thing is z, this thing on the right-hand side is x, and similarly we can plug in our simplifications for B2. So B2, we have this equals this after we refer to our simplifications. In B1, we can simplify a little bit more. We can observe that if we take our z here, so this is our z, and then we take off the last term in the sum, and then add up all the other terms separately and do the same thing for x. So this is x, take off the last term in the sum, and then add up all the other terms separately. Then we can recognize that the last terms in these two summons are equal. So to say that z is equal to x is equivalent to saying that these two sums are equal. So we can refer to this, the condition where these two sums are equal as B0. So we observed that B1 is equivalent to B2. We're now observing that B1 is equivalent to B0. Law of syllogism, which is essentially transitive property, then gives us that B0 is equivalent to B2. So that's what we have here. So given that 1, and therefore all of these equalities, B0, B1, B2, are satisfied, in particular, from B2, we have that this function is a periodic polynomial in x. All right, so let's see why that is. So B2 is this equality. The only difference between the left-hand side and the right-hand side is that the right-hand side, we replace x with x plus 1. So it's a periodic polynomial in x with a period that divides 1. But the important part is that it's periodic, because any periodic polynomial in x must in fact be constant with respect to x. And let's motivate this B0 a little bit as well. So this B0 in disguise is actually the punchline that we're getting at. It's this thing, this capital P sub n of x plus 1. Once we refer to our definitions, we see that is k equals 0 to n of little p sub k x plus n plus 1. So B0 is, in fact, what we're after. We're trying to show that star n is equivalent to B0. But it's helpful to know what B0 is equivalent to. So we observed that it's equivalent to B2. And B2 tells us that we have a periodic polynomial, so it must be constant with respect to x. But that's being constant with respect to x is what it means to satisfy star n. Okay, so we've succeeded in showing that this satisfies star n. And we're using the little p's here just because that was the notation we were using before. But this set is the set of capital P sub k of x. The statement that we were working with was if and only if. The converse is more straightforward. If we start with this set satisfying star n, well, then by definition, we know that this function is constant with respect to x. So if it's constant with respect to x, then certainly if we add 1, it doesn't change anything. So if we have star n, then B2 is automatically satisfied. But B2 is equivalent to B0, so we must have that B0 holds true as well. So then that gives us both directions, star n, if and only if B0. Okay, so that proves that result. There's a trivial solution, the set of just all 0 of capital P sub k of x from k equals 0 to n is just, they're just all zeros. That'll certainly satisfy star n, which we can see. We plug in 0 here, then this function would become identically 0. A function that is identically 0 is, in particular, constant with respect to x. So set of all zeros would satisfy star n. It would just be a trivial solution. If we look at non-trivial solutions, which is to say one of our capital P sub k's of x is not 0, and if we're in the case where f is a field of characteristics 0 or greater than n, so if we're dealing with rationals or real numbers or complex numbers, that would be the case of characteristic 0. So if we're in this situation, then it can be shown that the last term in this set, the capital P sub n, the x plus 1, is not equal to 0. So if one of these things is not equal to 0 and our field is the appropriate characteristic, then capital P sub n of x plus 1 is not equal to 0. And that's the same thing as saying capital P sub n of x is not equal to 0, but it's interesting to comment on the capital P sub n of x plus 1 because that's what shows up in our lemma. And if we know that that's not 0, that means that we're allowed to divide by that term, which is helpful. Okay, and then we can get one more result here, which we won't really be proving any further results, but we can talk a little bit about where they come from and applications that we're able to get out of this work. So one more definition here. For I sub nk x equal to this thing, we can use the concept of polynomial interpolation to prove the following lemma. Okay, so we have that this thing is equal to f of y. In particular, we see that this function on the left-hand side is constant with respect to x, which means that we satisfy star n. So we can use this result in combination with our previous results to get this following theorem here, which is a more tidy way of establishing an if and only if condition for star n. I'll briefly comment on how this result is proven. Polynomial interpolation is the idea of n plus 1 points uniquely determining an n-degree polynomial. To prove this, it suffices to show that limit as x approaches minus k for k equal to 0 up to n, this equality holds. So typically with polynomial interpolation, you're dealing with n plus 1 points uniquely determining an n-degree polynomial. It also suffices to work with limits, however. And since we have x plus k in the denominator, we would need to think about it in terms of limits if we're looking at x approaches minus k for values of k from 0 up to n. And this is not if and only if, but we can use this result in combination with our previous lemma for star n to get a more convenient if and only if condition. So for f, a field of characteristics 0 or greater than n, a set of polynomials capital P sub k of x, k equals 0 to n, will satisfy star n if and only if there exists a polynomial g of x such that for every k from 0, 1 up to n, we have this equality. So there are many applications of this theorem, one of which is the generalization of Worpitzky's identity, which states that for this function, we have this equality. And this might seem like a random function, but it's important in the context of combinatorics. This is not usually how the function is defined. A in k is usually defined as being equal to the number of permutations of the numbers 1 to n, in which exactly k elements are greater than the previous element. But fortunately, it does have this nice closed form, which we can make use of. And we're able to make use of our theorem by slightly generalizing this combinatorics related function, make it into a polynomial. Instead of having k minus j, we can have x plus k minus j. And this corresponds to the choice of g of x equals x to the n in our theorem here. And when we're using star n is a condition that relates to polynomials of degree less than or equal to n. But fortunately, this x plus k choose n, this is a polynomial of degree n. So we're able to use star n on this guy. Star n tells us that things are constant. So here, when we tack on this extra variable y, nothing on the left-hand side changes because our set of all these a's will satisfy star n. And so that gives us this nice generalization here. There's several other nice applications for this theorem, but we'll stop with that for now.